Hi, my name is Prislan, and I am presenting the results of our recent studies on weather-growth relationships to better understand the influence of changing climate conditions on xylem formation in beech in the next decades. European beech is a common and widely distributed species growing on sites with diverse climate conditions. In Slovenia, beech forests represent the most widespread forest communities. They are found on almost 90% of the total forest area, representing almost a third of the total growing stock. Due to its abundance, beech is highly ecologically and economically important forest species in Europe. Therefore, it is particularly important to understand how anticipated climate change will affect the growth of beech in the future. In Slovenia, a transitional region between Mediterranean, alpine and continental climate conditions, recent trends show pronounced warming which is twice as high as in the neighboring countries. The climatic observations of the past decades show warming around 0.3 degrees per decade and a decrease in precipitation by 3 to 6% per decade. These trends are in agreement with the predictions that annual temperatures in Slovenia may increase by 2 degrees Celsius in the next 6 decades. In case of precipitation, changes are expected in distribution rather than amount, with most precipitation in winter and drought in summer. In the past years, wood formation was studied in beech, but also in Norway spruce at 2 different sites in Slovenia. The main advantage of wood formation studies is the high temporal resolution of the data, allowing better understanding of wood formation phenology and growth dynamics. Long-term monitoring of wood formation, however, allows to quantify more precisely the relationship between environmental factors and xylogenesis. In this study, we used our wood formation datasets to evaluate climate growth relationships in beech and to predict xylem formation phenology and xylem increments under climate change scenarios. We hypothesized that due to warming and a decrease in precipitation during summer, growth season will be shorter, resulting in narrower xylem increments in the next 6 decades. The wood formation monitoring was conducted at 2 beech forest sites at different altitudes. A low elevation site, Panška Reka, located near Ljubljana, approximately 400 meters above sea level, and the high elevation site, Menina Planina, located in the Alps at 1,200 meters above sea level. At each site, 6 dominant, healthy adult beech trees were selected with a diameter around 50 centimeters. Microcores of stem tissues were collected during the 9 consecutive growing seasons between 2008 and 2016. The samples were prepared according to the standard procedure for observations under light microscope. On each sample, we measured width of the current xylem increment. In addition, we recorded the phenological phases of xylem formation, which included beginning of cell enlargement, beginning of secondary wall formation, first mature cells, cessation of cell enlargement, and cessation of cell differentiation at the end of the growing season. With the help of the Gompertz function, we evaluated the date of maximal cell production. During the 9 years of observations, beginning of cell enlargement occurred in the middle of April at the low elevation site and approximately 1 month later at the high elevation site. Cessation of cell enlargement and therefore cessation of cell production was observed in the first half of August. In this case, the difference between the 2 sites was much smaller. At the high elevation site, it was observed on average just a week earlier than at the low elevation site. Cessation of cell differentiation at the end of the growing season was observed at the beginning of September at both sites. Growth rings were on average 2 times wider at the low elevation site than at the high elevation site. To evaluate weather growth relationships, partial least square regression was used, where monthly maximum and minimum temperatures and the sum of precipitation were considered as predictors, and phenological phases and Xylem ring widths were included as dependent variables. To build a model which explains the highest proportion of variation of the dependent variables, a two-step approach was applied. In the first step, all predictors were included, and in the second step, some predictors were excluded based on correlation coefficients and variable of importance in the projection. Finally, the model was built with 7 dependent variables and 24 predictors. The best prediction was achieved with 2 principal components. The established model explained 73 and 71% of X and Y variables respectively. For spring phenological phases, the highest negative correlations were with maximum April and May temperatures and minimum March and June temperatures. The precipitation of May showed the highest positive correlation. Beginning of growth occurred later in case of lower temperatures and high precipitation in these months. Autumn phenological phases and Xylem ring width showed a negative correlation with maximum temperatures at the end of summer and positive correlations with minimum temperatures between previous autumn to current spring. High correlation were also observed with precipitation at the beginning of the year and in summer. The best fit between predicted and actual data was observed with spring phenological phases. Due to differences in spring phenology between the high and low elevation site, actual data are distributed in 2 distinct groups, but showing the same trend. Data of phenological phases in autumn and Xylem ring widths are evenly distributed along the regression line. At the end of the growing season, the best fit was observed for cessation of differentiation and the worst for the cessation of growth. In all cases, the studentized residuals were homogeneously distributed around 0. Afterwards, the model was used to predict changes in Xylem phenology and Xylem ring width in the next 6 decades according to the climate change scenario. The overall impact of the weather factors shows that in the next 6 decades, onset of growth may be observed in average 12 days earlier, where cessation of growth may be observed 8 to 11 days later. The duration of the growing season was estimated to increase by around 20 days at both sites in the next 6 decades, which will result in final ring widths wider by 83% at the high elevation site and by 38% at the low elevation site. Besides predicting the future, the model can also be used to evaluate spatial variability in Xylem formation. Here, a high-resolution grid of weather data for Slovenia was used to predict onset and cessation of cell production in different regions. The data show, for example, that in the Alpine region, the onset occurs later and cell production finishes earlier. To conclude, our model predicted longer growing periods and increased increments in the next 6 decades for beech in Slovenia. Therefore, our hypothesis was rejected. The growth of beech is expected to increase under climate warming on sites characterized by abundant water availability. However, we still need to evaluate the influence of extreme weather events such as late frost events and heat spells on Xylem formation. One of our next tasks is also to compare the performance of beech and the Norway spruce under climate change. Thank you very much for your attention.